Abrahamson. Dor is a professor of learning sciences and human development in the Graduate School of Education at the University of California in Berkeley. Dor directs the Embodied Design Research Laboratory. His work examines how students come to understand mathematical concepts through guided, collaborative, physically interactive encounters with artifacts and technologies. And his work draws on embodiment, cognitive science, and socio-cultural theory. He is widely recognized for pioneering the Embodied Design Framework, which shows how sensory motor coordination and bodily experience can ground formal mathematical reasoning. So please join me in welcoming Professor Dor Abrahamson. Thank you.
And thanks to Digital Futures for inviting me and hosting me here. I'm having a great time. It said I saw on the website that you're getting a free lunch, but of course there's no such thing as a free lunch, so you need to hear me talk. And the title Embodied Design is this, as Richard mentioned, is the framework or paradigm that I've been developing over the past, I guess, 30 years. Ugh, that dates me. Where essentially, this is leveraging evolutionary capacities as resources for mathematical understanding. It's this ongoing dialectic that I'm trying to foster. On the one hand, people come into the world with their basic capacities in their DNA, their epigenetic capacities that come from evolution shaping our DNA over millions of years, capacities to interact in the natural and cultural ecology, capacities such as perception to make a quick judgment of situations, capacities to learn how to move in a new way, such as to crawl, to walk, to run, to pole vault. And then on the other hand, there are these mathematical understandings. You'll see later I'll be using these two hands. So you have the evolutionary capacities, you have these mathematical understandings, which take a very techno-scientific formal look at the same kinds of phenomena. And in order to understand them, you really need to transform how you are perceiving situations. It's no longer these quick decisions such as, which hand has more fingers, well done. But you need to switch into a different way of thinking. Oh, counting 1, 2, 3, 4, and 1. It becomes formal. It involves language. It involves concept. It involves symbols, signs. So I'm looking at this kind of dialectic that I'm trying to foster and forge and organize through the paradigm between, on the one hand, these evolutionary capacities for making quick judgments, and on the other hand, these formal ways at looking at the very same phenomena. And the thesis here is that in order to deeply understand mathematical concepts, we as designers, as educators, need to create and facilitate occasions for students, for learners everywhere, to somehow coordinate between these two resources, somehow to ground the techno-scientific mathematical ways of seeing the world within their evolutionary capacities. So that's what the talk is about. And it just so happens that about 90 years ago, in this very place in Stockholm, a poet called Karin Boye, heard of it? Basically said the same idea. Just in one poem. So if you get the poem I'm about to recite, then you can just leave, because it's essentially that idea that knowledge is not something that you can kind of just take or just have or own as a commodity, but rather you need to transform yourself in order to and immerse yourself in order sort of to become the knowledge, in order to change the way that you yourself perceive the world. So this is how the poem goes. Let's see if it works. So, kunskap av Karin Boye. Alle de försiktiga med långa hovar träffar havets jätterskratt. Vänner, vad söker ni på stranden? Kunskap kan aldrig skönjas, kan aldrig ägas. Men om du råkar som en droppe faller i havet att upplösas, färdig för all förvandling, då skall du vakna med perlemorhud och gröna ögon på ängar där havets hästar betar och vara kunskap. All right. Actually, she's an interesting person. She was born in Gothenburg, but she studied to become a teacher in Uppsala, and then came here. And I don't know if she did any teaching, but certainly wrote many poems. So here we go. I come from Berkeley. And this is the moment where the technology suddenly doesn't work. And then you do this, then you put it back in. Then you hope for the best, and you make sure it's on. And never mind. So work here. Is it going to work at all? Okay, there we go. So I come from Berkeley, and my lab is, yeah, this is not working. Oh, there it is. My lab is about here. That's San Francisco. If you look closely, you'll see my lab. I live somewhere about here, which you cannot see. And so I run this lab called the Embodied Design Research Laboratory, which works in the design-based research framework. It basically means that we conduct our educational research within the context of research and development of artifacts. So we are passionate educational designers, but we're also researchers. We do our research in the context of ideating solutions, engineering them, building them, implementing them, trying them out, gathering data, analyzing it. And through that, we try to contribute both to theory by seeing new things that haven't been discussed or researched before, even as we are contributing to practice the prototypes that the lab produces. And at a kind of meta level, also trying to contribute to the very art of design, like reflexively creating design frameworks. This is the team. We recently celebrated 20 years. So as the proverb goes, we got the T-shirt. They keep changing. I'm the only one who remained here. And so our broad questions and all kind of big words, in terms of ontology, we're asking, what is mathematics? That we can know it. Questions in epistemology. What is the mind that it can know mathematics? Right? And semiotics, we're asking, what is the meaning of mathematical concepts? So these are very broad questions. And when we talk about meaning, as when educational designers wish to make mathematics concepts meaningful for students, what are we actually talking about? Phenomenology. What is the experience of meaningfully understanding a math concept? And pedagogy, of course, given answers to the above, how should we teach mathematics? And design is where, you know, the rubber hits the road. We ask ourselves, perhaps we can begin to answer all of these questions above through engaging in R&D of experimental pedagogy. So there's a kind of a cycle here where all these questions lead to designing solutions to educational problems, but then in turn, the design, the work of designing, thinking through, ideating, trying things out, gathering the data and finding like unexpected things, all of this leads back to answers or like attempting to answer all of the above. So there's a cycle which the following picture should show more nicely, better than that one. So I like to use MC Escher's picture, probably one of the most used pictures in presentations, where I think of the theory, educational theory, cognitive sciences, as informing the design of educational solutions. But then the work of the design, in turn, the design and evaluation, informs back into theory. So we're looking at the cycle where it's conjecture-driven work, like what if we tried that? What if only we created these conditions for learning, conjecture-driven? And it's iterative, these are empirical study wherein the theory and the design, they co-inscribe each other. And we use all kinds of media. I'm very happy to work with paper or just marbles or Lego or what have you. But we find ourselves working quite a bit within the design-based research framework with all kinds of technologies. So we've been involved in all kinds of projects. And I'll only be talking about two today, but just to put a few things here, this is using a multi-touch tablet in order to learn about proportion interactively. This one is for deaf students to learn how to sign mathematical concepts, right? We create this continuity, semiotic continuity or phenomenological continuity from the objects that they hold to the ASL or the International Sign Language. So we try to make the mathematics and the language continuous. Or what else do we have here? This is recently for blind students to learn geometry. We have this quad, and they can speak to each other through Zoom. And the quads, it's called teletangibles. When I move one, it changes the other one on the other side of the world in the hands of the student, who can then change it, and it changes this one. So these are machines that speak to each other, teletangibles. And so you might be seeing a theme here. We work a great deal with students of all kinds of diversity, sensory diversity, motor diversity, cultural, linguistic, and so on, both for ethical reasons that they are underserved, but also for selfish reasons that we learn so much about our own perception and action and sensation by working with a diverse crowd of people who bring differences and different kinds of strengths to the table to work with us. This is for children with sensory regulation needs, where we created a rocking chair, bought it from IKEA. The rocking chair, that the rocking itself changes the graph so that children with sensory needs who need to move a lot can be integrated into the whole class, with all the classes doing that together. What else do we have here? This one is for students with CP, cerebral palsy, to learn to communicate certain kinds of classes of vocabulary. This is cultural diversity. This is work we're doing in Bali, Indonesia, working with their cultural practice of dance in order to ground ideas in geometry. This is for children with learning disabilities. It's the system called Sensei that projects interactive floor and interactive wall. Children coordinate between these and work with tablets in order to learn basic arithmetic of things like 3 minus -2. What the heck does that mean? So to experience that. What else have I put here? We're working with Navajo people, indigenous native people of Southwest United States of today, to ground ideas of geometry within their ancient cosmology. And we work a lot with teachers. This is a giant icosahedron that we've built for both for students and for teachers' professional development. So this, I'm just putting here like a little selection of things that we do. This is a project I have right now going on in Poland, in Warsaw, a giant digital tabletop for two people to move an object through a maze, where one person can only move it this way, the other person can only move it that way. So they need to move together in order to move it through. So it's like a cross between Etch-a-Sketch and mini golf, if that makes sense to you. So it's this wonderful digital tabletop, and we're collecting lots and lots of data from there. Actually, there might be a future for that for digital future. That's another conversation. Anyway, all of these things that we create, we're working intuitively on one hand, but on the other hand, it's all based on principles and theories and philosophy of enactivism. And John Searle said that because we do not understand the brain very well, we're constantly tempted to use the latest technology as a model for trying to understand it. And I think it's really important to have a sound grounding in some epistemology and theories of learning to inform our design and research development of the artifacts, because it gives us a framework through which to think and through which to articulate principles for design and to make sense of our data and to build a community of global thinkers who share an affinity to the same way of thinking, the same way of conceptualizing the human mind. So in history, people used to say the brain is like a catapult, because that was like the latest technology. Because we don't understand the mind, so we use these machinery as our metaphor. The windmills of the mind. It's like some kind of circuit. It's like a switchboard. Oh, the brain is like a computer. Well, in the 20th century, people talk about the brain is processing information and abstract propositions in the brain and all kind of procedures. And yet, when you use brain imaging, we haven't found those. The abstract propositions and symbols have not been found. So maybe all of these metaphors don't work. So what might we work with? And so classically, and certainly in the 20th century, people have thought of the brain as something that is like disconnected. It's not connected. It's not a modal. It's not any modality. As if the brain works this way, where we get sensory information of like touch and taste and smell and sight and sound, and then all these things go into the brain and they transform into these abstract symbols that have nothing to do with the body, and then we come to an idea, and then back to the body. But it turns out things are not that way, and the paradigm is shifting in the cognitive sciences towards what we're calling embodiment, embodied ideas, embodied philosophy. And within the embodiment, which is kind of a large family, sometimes a happy family, sometimes not so, enactivism is the type of philosophy I'm most interested in. And we believe that all happens at the same time, that the mind itself is modal, that all cognitive activity is sensory motor. Tacitly, even if we're not conscious of it, we're always moving our motor cortex, and motor cortex is all the time active as we think, as we imagine objects, as we simulate actions on them, even if we're not aware of it. And we can actually get to it through a paradigm called neurophenomenology, which is some of the work that we do. So if we think about the mind as such, not as some kind of computing device, but instead as inherently sensory motor, then it makes sense to get back to the title of the paper, right? We should work maybe with the evolutionary capacities of how the brain is shaped through adaptively to our natural and cultural ecology in order somehow to ground the mathematical ideas. And we see this also in testimonies of professional mathematicians. This is Terence Tao, arguably the leading mathematician of this era. He got a full professor at the age of 24. I take personally as an affront, but he's very generous in speaking to the community, speaking to us in Math Overflow. We're like, how do you think? We ask him, and he says, it's all these crazy images. I was thinking like partial differential equations. It's like this egg that's on the oil and these frequencies, or maybe it's like a jet ski. And he says sometimes I had to lie in my office on the floor and roll over to get this idea of how to gauge these transformations. Very picturesque. Even back in 1945, Jacques Hadamard, a psychologist and scientist, put out this book in which he had interviewed all the leading mathematicians and scientists of Europe at the time, asking them, how do you think? People like Henri Poincaré and Albert Einstein responded, it's these images, it's all imagistic. Of course, we need to write things down, and that helps us, but essentially, it's these images. So we have all these testimonies. We have empirical work in cognitive psychology. The paradigm seems to be shifting towards an embodied perspective, and that has implications for education, for the learning sciences, which is the work that we are doing. So a colleague of mine, Art Glenberg, he was critiquing educational technology that are not sensitive to what he calls biological cognitive systems. And he said the following, one could view most of my reasons for skepticism with most educational technology as challenging for future development of technology that is sensitive to the principles of biological cognitive systems, right? You need to know how a biological cognitive system works, and the enactivist or the embodied paradigm speak to the biological cognitive systems as being inherently sensory motor, about interaction, about these transforming the perception for action. So that's what we're trying to work with. Technology that's sensitive to the principle of biological cognitive systems. So what are these principles, right? What are these things? How can we get to them? So enactivism, the theory from Francisco Varela, a book that came out in Berkeley in 1991. He was a Chilean biologist and philosopher, was strongly influenced by Far Eastern traditions, Buddhism, etc. This is the 2 points of enactivism. The first one is perception consists in perceptually guided action. Since we were millions and millions of years ago, before humanoids, when we were just single cell, 2 cell, tiny little things in the water, it was always the case that it was useful for us to know what's around us, right? So in order not just to move around motorically, like mindlessly, it kind of helped to know if we're moving towards something we can eat, or maybe something we should run away from. Maybe we can smell things or touch, etc. So all these sensations, our sensory organs, arguably developed in order to inform our actions. So inherently, when we perceive a situation, it's never perception, it's not a photograph, it's always perception for action. I see this object, to hold it, even if I don't mean to hold it, I look towards it, or maybe I look at the seat, I see it for to sit. Perceiving the affordances, as Gibson called it. So that's the first principle. Perception is always perceptually guided action. And then the other one, which is, it took me a few years, I'm still trying to understand this. Cognitive structures, or what you might want to call the neural substance of concepts and understanding, that which we learn, that which changes neurally, cognitive structures emerge from the recurrent sensory motor patterns. Okay, we're doing something over and over until it's task effective, that enable action to be perceptually guided. So if many times in my life I was trying to, as a baby, I'm trying to grasp this as a baby until oh, this one is working, this one is working. These are the recurrent sensory motor patterns, and they emerge. So more and more a cognitive structure is built in my mind. So when now I look at this, I already feel the affordance. It's perception for action. As a designer, I said it took me years. It's this nested kind of sentence that it's difficult to wrap your head around. But as a designer, I ask myself, if I want to work with this, well, what are the concepts or what are the cognitive structures I want to work towards? And therefore, what might be the perceptually guided actions that I create for students to enact and learn through? And what is the kind of sensory motor pattern? What is the exploration that I want to enable? Hopefully all of this will make sense. We find this useful to speak at least once people know our project, but hopefully moving forward will make sense. So once again, we're working from a certain kind of theory, from enactivist theories of the mind in order to inform the design. And these are cycles where theory informs design, and then design in turn informs theory. And I want to talk to you today about 2 projects. Each one of them, it represents a different aspect of what I'm calling the evolutionary capacities. I'll speak about them briefly. So I like to use this metaphor, and now you can see the 2 hands. I kept on doing this and that. You see where it's coming from. I'm just plagiarizing Michelangelo. So, oh, sorry. So I invite you to think of this as the kid, the student, the person who comes into the world with all the epigenetic inclinations, the capacity to interact with the natural and cultural ecology, depending where they're born and what, but they are ready to work with that, something that's been shaped through evolution, through millions of years. And then on the other hand, there's this, I call it culture or teacher that comes and says, hey, yeah, but you need to think about things in this way. It's all very well that you can quickly see numbers, quickly see all kind of things and make judgments according to your evolutionary capacities, but civilization has moved forward so fast. If you want to send a rocket to the moon, you need to kind of adapt another perspective, another way of looking. But we don't want you to lose your own way of looking. So we need to, well, this is me talking now. We need to try to forge some kind of dialectic between the two. And that's what the lab is trying to do. So I'm focusing on this connection. I'm always amused in this picture that God was way up there. But if you look closely, the Adam's hand is above, has the upper hand, you see? So I'm focused on this connection between the two. And so we speak about the biological cognitive systems that the child or the learner brings to bear. And I want to give you some examples. So if you look up here, okay, look again, here goes. And I'm going to ask you, which arrow moved faster? It's a bit choppy here. It should be nice and continuous. But, all right? So, right? And now the point is, hopefully you'll agree the blue one moves on. The thing is that I can say, oh my gosh, you're so smart. Because what you did is you calculated the distance, then you calculate the time for each one, then you divided the distance by time, right? Amazing, you did these calculations. Then you had two numbers, then you compared them. No, I don't think you did that. We just see that, or try this. Which line is steeper? I hope you just see which line is steeper, right? And I don't think you did any great calculations of it. Actually, it hits the cortex, and we have specialized cells for each steepness. We just know. Or maybe which box is denser? Ready? There's going to be two boxes here. Bam. Right? You just saw that. You didn't have to count, then divide by the space for each, and then compare. We just know that. So biological cognitive systems are amazing in doing that kind of thing. But it's not analytic. Mercifully, luckily, it's not. Otherwise, how would we're not calculating in our head all the time that way. But how about this? This is when I get nasty. It's like, which one is steep? So this is what I mean is, it's all very well to make these judgments, but now we want to send a rocket to the moon. It's just not enough, this machinery, this capacity that we have. And so then we need to bring in the mathematical cavalry, the cultural forms. And we say things like, okay, need to measure the height and the width of this one, and the height and the width of this one. And then we need to so we need to gauge them, and then to measure each one, and then we need to divide, because without this, we won't really know. Our ecological capacity can take us, evolution capacity can only take us so far. If we want to go beyond that, we need all of these kinds of calculations in order to arrive at, finally, this is, I remember I changed it by 1 degree. So, but the thing is, here's a very important point. When you bring in these cultural forms, invariably, always, you are asking the student to attend to certain properties of the phenomena that they had not been attending to. In this case, the projected height, the projected width. And yet, beforehand, you weren't doing that. You just saw that one was. So in every case, when there's this dialectic between biological cognitive systems and cultural forms, the cultural forms will be inviting or demanding that people attend to properties of the phenomena that they weren't looking at before. And I'll be giving more examples. And then the big question is, well, how can we both maintain these kinds of basic ways of looking at the world, even as we introduce these cultural forms, and in this case, measurement and calculation? What's my next slide? Oh, yes. So we're focusing on this point, and we're asking ourselves, what is it that we can create in a learning environment, specifically what technology, writ large, we can create in order to facilitate this productive dialectic between biological cognitive systems, and cultural forms, so that the students will understand, okay, will have a grounded understanding, for those who know Stephen Harnad's work on symbol grounding, so that the mathematical symbols will be grounded in some kind of visceral, intuitive meaning, some understanding, not something that you write, that you catch, or you need to become the knowledge. So the paradigm is called embodied design, and will be, so this is trying to answer Art Glenberg's early thing, future development of technology that is sensitive to the principles of biological cognitive systems. And the basic idea that you experience something first, and only later you signify it, right? First come experiences without any symbols in order to solicit from you your evolutionary capacity, and then pushing it to the point where you want to adopt, like before, where you just feel you need to adopt the mathematical way of reconfiguring the situations, of reperceiving the phenomena in question, and we look to see how this dialectic might work. So edrl.berkeley.edu, that's where you find us. And so one kind of work with two genres I'll be speaking about in the remaining time. One of them, I call it the perception-based genre of embodied design, which was this one, which draws on your evolutionary capacity to make these quick perceptual judgments of what's in math is called intensive quantities, or in physics, intensive. It's expressed as something over something, this over that. There are many situations, like with the density, number over space. So perception-based genre is the one that I demonstrated before, but I will also be demonstrating another one, which I call the action-based genre of embodied design. And that one is depending on your capacity to learn how to move in a new way. Just like babies learn to crawl, they learn to walk, etc. And if I can use this picture kind of reflexively for a moment, it's when two people need to touch their fingers, they're doing that. They're kind of figuring out how to move in a new way that they've never moved before. And we look to see also how people tend together collaboratively to enable what's called the joint action. So collaborative solutions to motor control problems demanding joint action. So that's the action-based one. And so I think this brings us to, so these are the two kinds of designs, perception-based and action-based. And I'll be demonstrating the perception-based through a project called Seeing Chance. And I'll be demonstrating the action-based genre through a project called Kinematics, or the mathematics imagery trainer. Wish I had 5 hours here, but let's see what we can do. So let's start with the Seeing Chance. So in the case of Seeing Chance, a perception-based embodied design, then always bear in mind this picture. I can't show it all the time, but this is the dialectic, right, between the evolutionary capacity and the cultural forms. So what I was looking for here is an answer to the following situation in the learning sciences. Tversky and Kahneman got a Nobel Prize for demonstrating that people are stupid. Well, you might, I'll use here like by way of simplification. If you flip a coin 4 times and you get heads and then tails and then tails and then heads, or maybe on another occasion you flipped and you got heads and heads and heads and heads. The vast majority of people, when you ask them, is one of these events more likely than the other, or what? The vast majority of people will tell you that this one is more likely than that one. But of course, it turns out that it's wrong, as all of you know. Right? It turns out that this is wrong because they are equally likely, these two events, because the coin has no memory. It's just not like, oh, I fell on a head, I better kind of now tails and maybe. But most people believe that, and so whereas they said, okay, this shows that you cannot trust people to think, calculate, and all that. Give it to the expert, the machine. But my senior colleagues and friends, Manfred Boroznik, Andy de Sessa, Gerd Giggins, Uri Brzezinski, and others, they said, well, wait a moment. You're telling me that the vast majority of people think this way? Shouldn't we ask at least why or what is going on? Well, it turns out that if you rewrite this as 2 heads and 2 tails, then it's actually true that this is more likely. In fact, it's 6 times more likely. So what it seems as if people are looking at this but ignoring the order. So just, sure, HTTH, but when you make these judgments of probability, of likelihood, we ignore the order. And that's what because that's our evolutionary capacity. This is how we see we are able to make these quick, even when babies as early as the work of Fei Shu, babies as early as 4 months old, 4 months old, babies as young as 4 months already can make these judgments looking at situations. Wow, okay? So we have this, but how do we bridge these things? And so I created a situation involving a tub with hundreds of marbles, half of them are green, half of them are blue, and this thing I call it the marble scooper. Oh, there's no sound. Okay, I'll make the sound. Okay. So you can scoop 4 marbles out, and I basically ask kids, what do you think will happen when you scoop? And kids are like, well, it's like half green, half blue inside. Yeah, so I think 2 green and 2 blue is the most likely thing you can get. Okay, but young children will ignore the order. They don't know that to do the combinatorial analysis, so they don't understand beyond that. But I start with, they make the correct prediction. I start by enabling them to get it right rather than get it wrong, which is what usually happens in probability lessons. So this particular design is ideated in order for kids to use their evolutionary capacity to get the answers correctly, even if it's not yet right. The experience first, they signify later, it's not yet analytic. But then I give them these resources. I give them these squares. Each square like this is this object, like an iconic representation of that. And I give them crayons, and I ask them, show me all the things that we can get. And eventually I work with them in order to create all the 16. And to make a very long story short, we create this structure. We create all the 16, and I put them in, and I call this thing a bridging tool. Why? Because it's like in combinatorial analysis where we do counting. You could just write, right? HTTH, HTHH, HH. You could write all of the things that like this way, horizontal. But here I'm using the actual images, like the icons from the situation itself. So it's a variant on the formal structure that I'm using in order to bridge between the evolutionary capacity of making these judgments and what will become this. Because some kids will look at this and say, well, we don't really need that because here are all the 5, because the order doesn't, because they're not looking at the order. But when they do that, they might go so far as saying, actually, I'm going to change my mind. I think they're all equal because look, there's just 5. So this is the kind of dialectic that we have here until the kids will look and say, but they say, oh, wait a moment, you know what? Yeah, you see, this is what I was telling you all the time. And I'm like, what? If you've been fighting me for an hour telling me the order doesn't matter. And they say, yeah, because you see, there's more of them. And there's more. That's why this one is more likely than that one. So that little moment where they make that insight, my entire career is on that moment in every single design. This moment of insight where and they make this coordination where they're able to perceive this display, which I take to be a mathematical model of the situation. They're able to perceive this display as meaning their intuitive judgment here. Between this visceral feeling, which is transmodal or amodal, this feeling of, 2 green, 2 blue is more likely. I just know it. I don't know why I know it. I just know it. Seeing this, suddenly they make us what I call a semiotic leap, the semiotic salta mortale. They jump from this feeling to imbuing the structure with And now the weird thing is, having done that, having created this product, now retroactively, they believe in the process. Okay, so it's a product before the process. Because having created this, they say, oh, okay, yeah, that's why we need to look at the order. Okay, so this is the perception-based embodied design. And so the phenomenon, and then coming to see this as a model of that. So in this case, we were working with young children. The marbles. Here are the cards. And here, agent-based models for doing the experimental frequentist approach. So 3 different approaches: the subjective, the classical, and the frequentist. And we were looking for connections between all the 3 of them. If there's no sound, then I cannot show you this. But what you'd see here is how this child, I call it Tamar. I don't think this the sound will work, but it's okay. Don't have much time anyway. In this conversation, I say to her, so you're looking at these 2, and you're telling me that, what do you think? If I take these 2, I say to her, is one of them more likely than the other? And you literally see her. This is on my website, so you can have easy access to this. She goes back and forth between saying, well, on the one hand, it seems more likely to get something that has 3 than something to have 4. And I say to her, yeah, but now you're talking about the whole group. These 2 cards. She says, oh, okay, so to get this specific one out of the 4, so maybe they're equal, like 50-50. Okay, then I say to her, tell me, are there any cards here that are more likely than another card? And she goes like, well, yeah, I think this one is just more likely than the others. I say, which one? She says like this, it's because 2 green. I said, wait, do you realize the confusion that's going on here? You're taking one card, but you're speaking about it as if it's the whole group. She says, oh, right, because it's this specific one. So what I do is I'm forging a dialectic, a conversation, a negotiation between the evolutionary capacity and the mathematical forms. I'm staging that dialectic as a negotiation of different perceptions, different perceptual constructions of an object, where she is seeing this as 3 green, and I am seeing it, well, yeah, but the specific one, ta. And I'm saying to her, you're never wrong. When you say those things that you are saying, it's because you are looking at this as 3 green, which is absolutely fine. Keep on doing that. Way to go. That's how we all do. That's how everybody does. Even people who study this all their life. We see it that way naturally. At the same time, we need to understand that the mathematical way, as I said before, the mathematical way of looking at natural phenomena will always ask you to attend to properties, just like with the line, with the height and width. Here it's property of order. It's inviting you to attend to order, which you had not been attending to. So that's a negotiation we have there. So in this case, when we focus, the kind of game that happens is, says, order matters, the teacher says that, right? And you need to know that in order to understand the binomial thing. And the kid says, no, order does not. And so we create this phenomenon for them where they viscerally understand and make correct predictions. We create the bridging tools, and make this phenomenon, and this becomes the model of that. And eventually the kid kind of decides, oh, okay, yeah, order kind of matters, because they, like retroactively, they get this. And I won't go into details, but in perception-based embodied design, I conjecture that the reason that they agree that this is a model of that, because they feel the inferential parity. They feel that this is giving them the same, they are able to perceive this as meaning the same inference as they had here. Okay, these things are less important, Brunner, etc. So that's perception-based embodied design. And I think that in the interest of time, I won't speak too much about, sorry.
Question.
Oh.
I was wondering about the previous example. What is the embodiment element? What is the sensomotoric, whatever? Where's the importance of this?
Yeah, excellent question. So the sensory motoric, when you shift into an embodied and active perspective on the mind, where all cognitive activity is sensory motor, it might be strange to see because they're not like moving in a new way that you can perceive. However, the first principle of an activism is perception is always perception for action. So when they need to perceive this structure as bearing the meaning that they had experienced here before, the perception is never just seeing this like a camera sees it. I'm perceiving this as enabling my action. In this case, the action is not a direct physical transformation of the environment. Rather, it's a perceptual transformation of what I'm seeing. According to an activism, there's no subjective reality there that we are coming to know, but rather we are constantly changing our perception through interaction. So across the various genres of embodied design, we take seriously that cognitive activity is sensory motor, and we look to see how action can be thought of more broadly, not just transforming the world concretely, but also in terms of the semiotic action. So action is the actuation of intentionality. In this case, and Jean Piaget also speaks about that. You change things either apparently or literally, right? And I think if we hold that question, thanks for the question, it'll. I have like these extra slides that I don't have time to show, where I compare the two genres. So let's see the second one. And again, in the interest of time, I have here kind of the Bible of how to create these kinds of things, the codex. But I might go forward to the next genre. But all of this thing is available. Basically, you take the concept of probability and you phenomenalize it in the form of this tub where kids can get it right. And then you take the mathematical model, which is counting, and you concretize it into that bridging tool. And then you create this the semiotic leap by the negotiation between the two. If anyone wants to photograph, I'll stand aside. But very happy to send these slides to anyone. But I do want to show the other kind, kinematics, and action-based embodied design. Now, this takes us back to... so this is like the old way of thinking about how the mind works. But good old-fashioned artificial intelligence cat. But we know from philosophy and linguistics and cognitive psychology, anthropology, dynamic system, and robot, that this is not the way the mind works. Because actually the cat is very happy. Yeah, you see this empirical n equals 1. Try it again. Okay, n equals 2. Yeah, it replicated. It can do very well without all of these calculations. This is the biological evolutionary capacity. You need those calculations, as I said, if you want to send a rocket to the moon. But how do we work with this, okay? So doing stuff is not what you think. You're able to do things without calculations of that kind. Here's work from Macbeth et al., how baseball outfielders determine where to run to catch fly balls. So it used to be thought that, okay, if you want to catch this ball, then you need to make all these calculations of where it's going to go. Wait a moment. Okay, hang on, ball, don't let it go. Got it. Okay, so now I can run and will fall exactly where I expected. Just need to put my hand and plump, it just falls there. Shifting away from this paradigm, we're looking to think about interaction in a more biological cognitive way. So what is actually happening, it turns out, you entertain this kind of, I'll call it an attentional anchor. You look, the ball is coming from behind you, wait, that direction. The ball is coming from behind you and you're running. And so in your perception, the ball is coming towards you, okay, it's coming towards you. If it's too high up from this line, you need to slow down. If it's too low, you need to hurry up. So your job is to keep the ball all the time on this line, and eventually it'll come. So this is something that mammals do, birds do. This is how they coordinate their flight in order to catch prey, in order to get to moving targets. So, well, okay, that's how you do stuff in the world, but how about math, right? So why am I saying that this has anything to do with math? So I'll try to show you in what sense I believe that this is related to math. So I won't get all the way to symbols, but I have slides for that if people are interested. But let's just look at what the children are able to do. So in this particular, in the action-based embodied design, this is the mathematics imagery trainer, where I've used all kinds of media, Leapfrog, Kinect, the tabletops, tablets. So this is just, it's like a design architecture that's been implemented in many different media, but this was the first one where we were hacking Nintendo stuff. So this hand controls this cursor, sorry, this sensor of this hand controls that cursor. You need to make the screen green. So what does it mean? You come into a room and somebody says, make the screen green, and you try this one and it's red, this one and it's red, both of them, and it's red, faster, slower. So, suddenly it's green. Why is it green? Because I've set things up so that the height of this and the height of that are a particular ratio. In this case, it's a 1:2. And as long as it's at that ratio, the screen will be green. So kids find one green and say, now what? I say, make another green. So they look around and there's no frame of reference, but they kind of imagine, well, this must be some method in the madness. And so they like move their hands up like that, okay? But when you move both hands up this way, of course, you violate the ratio. It has to be lower, so it becomes red. And so the kids kind of, they fix it back to green, then move up again, they fix it, move up again. Eventually they say, wait, like I'm always, as I go up, I keep on, okay, let's prefix it. And they kind of, you actually see the adjustment, and then they start moving smoothly. And in papers, several papers we've published, which I don't have time to show, we've used recurrent computational analysis. Sounds wrong. Recurrent quantification analysis, RQA, in order to demonstrate that the shift from one way of moving to another way of moving, to proportion, can be modeled as a phase shift between two attractors. So we bring to bear complex dynamic systems analyses in order to understand mathematical insight as a shift from one way of moving to another. Just like a horse is walking and he puts more and more energy, it gets into this transition, then it starts trotting and eventually galloping. So we are able to measure using eye tracking and hand movements, triangulated with clinical data of what the students are saying. We are literally able to capture the moment of transformation between one way of moving and another, correlated to a mathematical insight, which supports the enactivist perspective. So what I want to show, so that they start just with these cursors and then enter symbolic artifacts. This is where remember, now this comes in, the cultural forms. We bring in these, the grid and then numbers, and children experience this functional parity, like, oh, wait, now I can move in a new way. They start noticing the lines. Oh, and they say to me suddenly spontaneously, oh, for every one I go up here, I go up 2 over here, 1 and 2. And whenever if I have one number, then the other one is going to be double. So we see this coordination, and eventually they can move their hands continuously, even as they appreciate that it's a multiplicative relation between the two. So once again, this is I think a more obvious example of the enactivism, because it's what's the word? It's overt, not just covert. For the covert, we use brain image, scan FNIRS and other things. So bridging over. So what I want to show here. How do the Beatles say, you're such a lovely audience, I wish I could take you home with us. Yeah, but don't have much time. So let me just show you something really cool. We took this one, and now we collapsed it so that one of them is going here. So in order to make the screen green, you need to move your hands simultaneously, orthogonally, and proportionately, right? It's not an easy thing. Usually when I ask people to do that, they go kind of like that. Yeah. So, and yet young children, this is in Holland with collaborators from Utrecht University, Arthur Bakker and other friends. We're using eye tracking to see where the child is looking. And I'll just take us forward in the slides. At a certain point, and again, there's no sound here, you can read. So you ask the kid, like, how are you doing this? The kid says the line has to, you saw that? It has to somehow rein in the line. And we didn't know what the heck they're talking about. Turns out what these young children are figuring out, it's difficult to move this and that. It's like these things we used to do as kids, right? It's difficult to move that, and they collapse. What's called dimensional compression. That's what Mike Richardson calls it. They collapse these two movements. The kids, they imagine a diagonal line. Can you imagine a diagonal line between my fingers? Check, 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 check. Everybody sees the line? Okay. Now look at this diagonal line, and notice how it's moving sideways. The line is moving, not the hands. Okay? So once they make the screen green in one place, they just keep moving their hands, imagining this line. And again, what I don't have time to show you is how we transition, that's kind of the following paper, how we transition from that into marking. We put a sheet of paper on that and they make lines, etc. So, and And once they can do that, we see marvelous things. So notice where their eyes are at the eye tracking. You notice that? They're looking not at their fingers, they're looking somewhere here because they're imagining where the line is going. Or some kids say they imagine they close this rectangle. And they keep on going back to the origin, so that actually their eyes are going along in a graph that is y equals half x in this case. So that's a case of they're witnessing this line that emerges for them out of nowhere, and this new structure, the diagonal line, emerges in the child's orientation towards the environment as a perceptual solution to the sensory motor problem of coordinating the co-enactment of two independent movements. So we literally see here how in the action-based genre of embodied design, we create laboratory situations. We occasion opportunities for students to construct new cognitive structures. And as enactivism said, cognitive structures that enable action to be perceptually guided. This line we call an attentional anchor, drawing on the philosophy of movement science from Hato and Raul Sanchez Garcia. This pops up into our mind as well. And so we believe that this is insight. And this is what I was promising before, to show you how these two issues are related, how we are creating for mathematics the same kinds of capacity as people create naturally and animals create naturally in the environment. So,
sorry, could you explain again this with this line?
Yes.
The angle?
This one?
Yeah.
This one?
Yes. What happens there with the?
All right. So, if I'm running towards, if somebody throws a ball from behind me, I don't play baseball, but and now I'm running to catch the ball. I'm not calculating anything. Rather, I'm perceiving the ball in relation to a diagonal line.
And you're trying to keep this.
Right. I'm trying to keep the ball coming
the
to
same
me.
angle. Okay.
Yes. Yes. I'm always, when I'm giving these presentations, I'm very careful not to stand like this. Somebody takes a picture. Professor Abrahamson, sorry, just Monty Python. So I don't have time to. I have these slides that are kind of showing all these principles, and as I said, I'm happy to share these things. We don't have time for that today, but maybe I'll just show a closing slide, a kind of statement thing. Okay, that's action-based. Yeah, learning is moving in new ways. Let's delete it. So a call to action based embodied design is mathematical concepts are grounded in mentally stabilized sensor motor patterns that emerge as attentional anchors, like the line, practical solutions for perceptually coordinating the enactment of ecologically coupled movements. Right? Cultural reframing of these attentional anchors, when we bring in the math, interdisciplinary analytic form, may occur through the timely, multimodal, multimedia mediation, speech, gesture, and symbolic artifacts. So that's when the cultural forms come in. And students adopt these new resources spontaneously as readily available means of enhancing their goal-oriented actions. Yet in so doing, they appropriate heritage conceptual systems that enable them to participate in the social enactment of mathematical practice. As design, we can engineer and facilitate the process. We have everything we need, so let's do it. And I think I have a final slide, just like a big colorful one. Where is it? I won't go through this. I won't go through that. And oh gosh, I'd hidden the slide, but you can never show enough stuff. Where was this? Yeah, I think I wanted to show just one more. Yeah, thank you. Well, no. Here we go. The brain is not a computer. It does not process abstract symbols or propositions. The act of thinking mobilizes the same sensory motor modalities by which we function in the natural and socio-cultural environment. How we think, therefore, depends on how we know to move in the world, how we know to operate on various objects, what tools we have mastered, what languages we speak. As such, educators can affect students' cognitive development by shaping their sensory motor experiences with dedicated objects. Thank you. Sorry, I've kept you over time. Yes, sir.
Yes.